Okay, so ladies and gentlemen, thank you very much. I would like, first of all, to thank I'm also very glad that I have the opportunity to, let me take the laser point, to, yeah, to convey you some of our recent investigations, which were devoted to shed light on the impact of so-called pneumatic fluctuations into the charge dynamics, specifically of optimally doped iron-based superconductors, for which we did discover a rather unprecedented, somehow emphasize the motivation for our recent optical work. And let me start with a very general concept of pneumatic phase, which arose as a central idea as far as high temperature superconductivity is concerned, particularly in connection with the pseudo-gap phase of the high temperature superconducting cuprates, and more recently, as far as the iron-based superconductors are concerned. The pneumatic phase refers to a phase where actually the electronic system breaks and discrete rotation remains preserved. And in this context, I would like to show you the phase diagram for the Aeropnectite family, so either the hole or the electron dope. But similar phase diagram actually can be obtained also for other type of iron-based superconductor. The point here is that there's, particularly in the underdoped regime, a tetragonal to orthorhombic phase transition, which indeed breaks the fourfold rotational symmetry of the tetragonal phase, and this was indeed ascribed to pneumaticity. Now, such a structural phase transition may coincide or eventually precede the phase transition into a magnetically ordered state, possibly due to some stripe magnetism. Now, the point that I would like to make here, and which is going to be of relevance for my presentation, is that there are several experimental evidences pointing out that there's a rather broad temperature interval extending above the nominal temperature for the structural phase transition, which is characterized by pneumatic fluctuations, and this all the way up actually to the optimally doped regime. Now, with respect to the pneumatic phase transition and pneumaticity in general, the DC transport properties and actually the anisotropy induced by an external symmetry breaking field in the DC transport properties were of paramount importance in order to shed light on pneumaticity. In fact, by measuring the DC anisotropy when you apply uniaxial stress, so by performing ferroelastic type of, or let's say, elastoresistive type of investigation, you can extract the pneumatic susceptibility, which is shown here for the family of the cobalt-doped 1 to 2 materials from the underdoped all the way up to optimal and overdoped regime. Such a pneumatic susceptibility turns out to diverge in a Curie-like fashion. And if you plot the Curie temperature as a function of this diagram, the star, actually the T star here, you see that it crosses the doping axis quite in coincidence with the optimally doped regime, which led to some conjecture that pneumatic quantum criticality may be very important here as far as the pairing mechanism is concerned, and eventually in order to enhance TC. Now, it was also found that these behaviors in iron-based superconductors for several different families and all the way up to the optimally doped regime. Now, in the past, and I did report also at this conference on our previous investigation, we were focusing the attention on the underdoped regime. But recently, we moved our attention to the optimally doped regime in order to investigate the impact of pneumatic fluctuation, because for optimally doped materials, the materials are always in the tetragonal phase, into the charge dynamics, which actually image the absorption spectrum related to the electronic band structure. And this over a rather broad temperature interval, which extend also to temperature into the superconducting regime, so deep into the superconducting dome, as far as the phase diagram is concerned, which is a regime which is not accessible with elastoresistive type of investigation. So because of that, we focus our attention on these optimally doped materials with a TC of 38 degree Kelvin. Now, the experiment consists in measuring the optical reflectivity, this over a very broad frequency spectral range, which extends from the far infrared all the way up to the ultraviolet, and as a function of two tunable variables. Obviously, temperature, because of the various phase transition, today because of the phase transition into the superconducting state, but also as a function of uniaxial stress, which turns out to be an important tunable variables, which allows you, first of all, to circumvent the twinning of the spacemen, particularly in the orthorhombic phase, because of the ferroelastic transition. So by applying uniaxial stress, you can actually detwin the materials and induce a single domain fully detwined phase, which allows you to appreciate any anticipated anisotropy in any physical measure. So when you apply uniaxial stress in the nominal tetragonal regime, you can exploit uniaxial stress as an external symmetry breaking field, which can allows you to stress induce some orthorhombicity. Now, we developed a mechanical stress device, which consists of a bellows, and by flushing helium gas in evacuating the same, we can exert or release stress on the spacemen, which were cut and oriented in such a way that upon applying stress, the domains preferentially align along the shorter orthorhombic p-axis, so parallel to the direction where stress is applied. And this allows us to perform optical experiment as a function of polarization of light along both stress-induced orthorhombic axes. Now, let me show you, first of all, the data which were collected for this optimally doped compound at 10 Kelvin, so deep into the superconducting state. TC here is 38, as I said before. What I'm showing you here with this color map is the measured reflectivity for both crystallographic axes. So with light polarized along the elongated orthorhombic axis or the shorter orthorhombic axis, which may be stress-induced, as I said. And as a function of the applied stress, which can be tuned in a controlled way, as I said before, in situ. Now, the data I'm going to show you now and for the rest of my talk were obtained after the so-called zero stress cooling protocols. It means that we reached any target temperature without applying stress, and then at that fixed temperature, we apply stress in situ, tuning it from 0 to a maximum value, and then releasing it back to 0. Now here I focus the attention on the mid-infrared down to the far infrared spectral range, because for the optimally doped regime, this was the spectral range where we did discover, first of all, some temperature dependence because of the superconducting phase transition, but also some relevant stress-induced anisotropy. In fact, you can observe that the measured quantity reached total reflection at very low energies. This is the typical signature in optics for the superconducting state. But particularly at the largest applied stress, you can already see here that there's an obvious polarization dependence, which is imaging an optical anisotropy, which is stress-induced. And interestingly enough, by releasing stress back to 0, basically you go back to the initial state. So that stress-induced anisotropy is fully reversed. We see here that upon applying a stress, you stress-induce an anisotropy, so a deviation from 1 in this ratio, which corresponds to the isotropic limit. But when stress is released back to 0, you go back to the initial state. Now, we did perform the measurement, obviously, as I said, all the way up to the ultraviolet, so at much larger energy scale, which is the prerequisite in order to perform reliable chromoelectronic transformations of the measured reflectivity. And this allows you to have access to all optical functions, like, for instance, the real part of the optical conductivity, which is shown here for both axes in the same spectral range as before as a function of the tuned stress. And here we observe some interesting features, this sharp drop basically to 0 of the real part of the optical conductivity, which later on will be associated with the relevant energy scale finite optical conductivity at the lowest energy spectral range, which we can reach with our experiment. These indicate some residual, or basically correspond to the high frequency tail of some residual Judah-like resonance, which is due to the itinerant charge carriers activated across the superconducting gap because of the thermal pair breaking. But again, you see here that upon applying stress, there's an obvious anisotropy. This can be observed if you consider the difference of this quantity between the two axes, which is a measurement of the so-called dichroism. And you see, in fact, that at energy scale around 60 millielectron volts, so very close to the Fermi level, you get a stress-induced anisotropy, which goes back to the initial state. So it is fully reversible upon tuning the external symmetry breaking field. Now, after I try to convince you at least that at that low temperature, there's a stress-induced anisotropy, let me focus the attention for the time being at this energy scale of about 60 millielectron volts, so 600 wave numbers approximately. And let me show you now with a color map the temperature dependence of this quantity, namely the deviation with respect to one of the reflectivity ratio read at this frequency. One, as I said, is the isotropic limit. Now, this color map shows you for this quantity the temperature versus applied stress dependence. And you observe, in fact, that you need to cross TC to go into the superconducting state to have a stress-induced optical anisotropy, which, however, turns out to be fully reversible by sweeping the external symmetry breaking field at any temperature. So even though there are some experimental evidence for a substantial nematic susceptibility and therefore for nematic fluctuations also above TC, this seems to be rather weak from the perspective of our optical investigation to be clearly detected. If they are present, there seems to be, in fact, very, very weak or somehow negligible. You can also now look to the dichroism here as a function of temperature for three selected applied stress, so the initial zero stress, the maximum applied stress, and then the stress released back to zero. And you see that, in fact, you have to go into the superconducting state to see a stress-induced anisotropy in the optical spectra, which, however, is reversible, as I said many times, when you release stress back to zero. The important things also to observe here is that the energy scale which are affected by the external symmetry breaking field are rather close to the Fermi level. So this means that the uniaxial stress is affecting the conduction bands crossing the Fermi level, and therefore of relevance for the transport properties, determining also the superconducting property. This is somehow at variance with what we have observed in the past on the underdog regime, where actually the stress-induced anisotropy was observed, even with an hysteretic-like behavior, by the way, was observed all the way to up to alpha electron volt away from the Fermi level, so rather deep into the electronic structure, which was indicating some important ferroorbital mechanism, or was somehow signaling some ferroorbital-like scenario driving the nematic phase transition. This ferroorbital type of coupling seems to be somehow negligible or not so prominent as far as the optimally doped regime is concerned. So let me now try, going toward the end of my talk, to elaborate a little bit on this energy scale. So let me show you the measured real part of the optical conductivity down in the far infrared, here for the state at the largest applied stress. So as I said before, you see here this rather important and substantial anisotropy in the optical spectrum between the two crystallographic axes. You may appreciate here this razor sharp onset of absorption. This is the typical behavior for a so-called S-wave-like superconductors, where actually the gap, although maybe anisotropic, open on the wall Fermi surface. Such a behavior can be very nicely accounted for or reproduced by the matte disparting approach, which is the conventional description of the real part of the optical conductivity for a S-wave-like superconductor within the PCS framework. And in fact, this is a very straightforward procedure, which is pretty well established in the literature. You can fit very nicely with this multi-sparring approach as the measure spectra. You can even reproduce very nicely in quite great detail the observed anisotropy. Now you may ask, but where this anisotropy comes from? Now, from the Raman spectra, we know that this is a gap material. There are at least two superconducting gaps. And in fact, we did apply this multi-sparring approach within a two-gap scenarios. There is at each temperature. So you can extract the temperature dependence basically of the order parameter of this superconducting phase transition. And you see that upon crossing TC, there's indeed a stress-induced anisotropy at the lowest temperature in the relevant energy scale of the superconducting state. That anisotropy is particularly pronounced for the largest gap of the two in these materials. So let me now try to approach the conclusion of my presentation, since I think I just have 20 minutes. So today I focus the attention on this optimally doped regime, for which we did discover a rather important anisotropy at very low energy scale, so in the far infrared, very close to the Fermi level, therefore. That anisotropy turns out to be fully reversible upon tuning the external symmetry breaking field, which is in our case a uniaxial stress. This behavior is just incipient at TC, but we were not able to observe any stress-induced anisotropy in the normal phase. The main implication of these results, as I just showed you in the previous view graph, is that there's apparently an anisotropy in the superconducting gap, which is the relevant energy scale of the superconducting state. And this may be considered as a smoking gun evidence for the realization here of a nematic superconductors. And with this statement, I like to conclude by acknowledging the great work of my team, actually my former team, my PhD, my postdoc, Arni Van Paal, and my former PhD student, Manuel Chinotti, the beautiful spaceman from the Stanford group by Professor Fisher, and last but not least, the financial support of our funding agencies in Switzerland. And then thank you very much for your kind attention, and I'm glad to take your question.
Yes, when you talk about this anisotropy, this is a very good result and a very nice lecture, by the way. Are you talking directly?
We do have an electron forming type of anisotropy, but actually the anisotropy that I show you, maybe I can go back to this view graph, that I show you here in the optical conductivity. Actually, what it does imply is an anisotropy in the suppressed spectral weight because of the opening of the superconducting state. And this suppressed spectral weight actually moves in the collective mode, which we cannot obviously measure directly in our experiment, of the superconducting state itself. And this should imply actually an anisotropy in the how can I say, in the penetration depth, but I'm not aware of measurement done in the same condition of this quantity. Actually, what I believe is that this behavior could originate from an anisotropy in the scattering rate, first of all, of the itinerant charge carriers. So driven by spin fluctuations, which turns out to be anisotropic in the nematic phase itself, in the stress-induced orthorhombic phase. And therefore, that nematic phase could be somehow vestigial of some kind of strike magnetism. Or the other possibility, because of the anisotropy in the spectral weight, there are in optics two quantities, the scattering rate, but also the effective mass. There are theoretical ideas proposing indeed a so-called orbital differentiation upon applying an external symmetry breaking field, which might lead indeed to an anisotropy in the effective mass of the itinerant charge carriers, which is then basically related and pairs with what I said before concerning the anisotropy of the suppressed spectral weight itself. And by the way, this orbital differentiation or differentiation of the effective mass seems to be further enhanced by correlation effect, which for whole doped materials are actually very important.
Okay, so I have one small question. Yes. So this is the cobalt dot, no, so potassium dot 1 to 2.
Potassium,
Yeah. Do you also do the experiment the other pnictite, for example, cobalt dot or nickel dot samples?
Well,
so your question is in the general conclusions of the pnictite optimal dot sample?
Yeah, this is a very good question. Actually, we would love to extend our experiment to many other materials. It's a very time-consuming experiment, by the way. It's not that easy because you really need a very well-characterized specimen cut and oriented in such a way which allows you to apply in a suitable way the external uniaxial stress. So this is ongoing, actually, but I don't have all the results. I hope that this is really very general. I suppose that this is general, but I don't have right now an experimental proof.
Okay, thank you very much.